everybody. Thank you for joining us for another session of EI Live K-12. My name is Cassie, and I oversee education and outreach activities for the Earth Institute. For those of you who are joining us for the first time, welcome. And for those of you who aren't familiar with the Earth Institute, our core mission is to foster a greater understanding of the science behind climate change and sustainability and what we as global citizens can do. The Earth Institute is actually quite interdisciplinary. It's made up of economists, business and policy experts, specialists in public health and law, and of course, earth and environmental scientists. The Earth Institute is actually made up of 24 or so research centers and several hundred people who collaborate across many different departments at Columbia University. And what we're hoping to do with these EI Live K-12 sessions is to introduce you to that interdisciplinary work through our scientific experts. We are continuing our series up until the end of June. And if you'd like any additional information about the remaining sessions, please don't hesitate to contact me directly. We also have all the recordings from all the sessions we have been doing since January 2021, as well as last spring, we actually did many as well. So today we're very lucky to have Dr. Chia-Ying Lee from Lamont-Doherty Earth Observatory. Lamont is the largest of the Earth Institute research centers and is responsible for the foundational sort of basic science research that informs all of the other applied research that many of the Earth Institute centers engage in. So she's going to be speaking to us about hurricanes, specifically how they grow, how they form, how they change. And she's also going to share some insights about what scientists like herself know and don't know about the upcoming hurricane season, which I believe is starting very soon. And so she's going to do her presentation, and we will also have a colleague from NASA's Goddard Institute of Space Study join us in a little bit to share some relevant NASA resources, and then we'll open everything up for questions. So for those of you who are tuning in for the first time, we don't use the chat box for questions, we use the Q&A box. So please make sure you type your questions there. And if there's something that pops up during the presentation you'd like to share that question, feel free to write a question in there at any time. So Chia-Ying, I'll hand it over to you.
Thanks, Cassie, for the wonderful introduction. And hi, everyone. Thanks for joining today's lecture. As Cassie said, today we are going to talk about hurricanes. So the animation here I'm showing you is a historical track from 2000 to 2012. And along the track, we can see the hurricane intensity. So this kind of image gives us a view of hurricane climatology, or you can think it as an average behavior of a hurricane. And from here, we see that the tropical cyclone forming from the warm open ocean, and there's a seasonality. So when there's hurricanes in northern hemisphere, you don't actually see that much in the southern hemisphere, and vice versa. There's a clear area, there's no hurricane, and there's some area that tropical cyclone or hurricane can reach a high intensity strength. So one of the reasons we choose to talk about hurricane this week is because of the upcoming hurricane season in 2021, which will officially start from next week, June 1st. Of course, hurricane can form before June 1st. And in fact, we already have one Anna this year. And if you still remember last year's crazy Atlantic hurricane season, we have multiple cases forming before the official starting date. So in preparation for the upcoming hurricane season, last week, NOAA Climate Prediction Center issued the 2021 Atlantic Hurricane Season Outlook. In this outlook, the main message they would like to provide is that based on the science, they predict 60% chance of the season to be above normal. What they mean is that they expect 13 to 20 named storms. Among these storms, 6 to 10 would be hurricanes. And among these storms, 3 to 5 will reach major hurricane strength. So in today's topics, ultimately, I would like to be able to explain to you, to the first order, what is the basis of NOAA-CPC and the scientists to provide such seasonal outlook. But we will start from looking at hurricanes from space and how does a hurricane look like when we cut it open, look at the vertical cross-section. And then we will talk about how hurricane interact with the environment, which is very important factors that inform us how we define the upcoming season will be active or inactive. So let's get started from get a definition terminology out there. Hurricane itself, which I mark here, is actually a local name for tropical cyclone. It is a tropical cyclone is a general term of low pressure system that originates over tropic ocean. So in Atlantic and the Eastern Pacific, we call it a hurricane. In the Western Pacific, it's called typhoon, and in the other area of hurricane basin, tropical cyclone basins, they just simply call cyclones. Now, in this satellite image, we see there are two systems already, two cyclones already, one in the middle, one is slightly outside of it. I believe this is an image I selected from 2017. So one of them is probably Irma. So you can see they kind of look they look similar, but there are some difference. And the effect by looking at the tropical cyclone from the space, we can have a rough idea how strong the storms are. So now let's zoom into looking at the individual systems. So the intensity of a tropical cyclone is categorized as tropical storm and the category 1, 2, 3, 4, and 5. Here is the definition of the categories is based on the maximum surface wind speed measured at each storms. So we can see when tropical cyclone is only have tropical storm strength, we do see some kind of cyclonic or counterclockwise circulation from the cloud image, from the visible image from the satellite. But we don't see the clear center, and there's like individual convections pop up more thick area here. But once it becomes a category 1, we start to see there's some kind of circulation center more clear, and then category 2 too. When the storm's eyes open, that's usually a sign of the storm is very strong. It's always become a major hurricane. So we can start to see a sign, the eyes in categories 3, 4, and 5. And once the storm becomes category 5, it's a very compact disk of cloud with a center of ice. And when the tropical cyclone, even when it's strong, if it passes through the land, then the convective system, the convections in the eye area may be kind of destroyed a little bit, so you no longer see ice. But if the storm can maintain strength, then once it leaves the land, you can start to see it try to reorganize. So the final image is a kind of quiz for you. Maybe later on you can tell me what's the intensity of the storms at the final stage here, showing in the corner figures. So now let's zoom in further, looking at the eye of the hurricanes. So this is the eye of Hurricane Dorian in 2019. What do we think here is a visible image of Dorian, and we can see there is a primary counterclockwise circulation that is called primary circulation. And then we also see at the eye, the cloud has like stadium, like a pattern. And that is because the convection at the eye area, like at the eye wall. So here is the eye of the storm. Here is what we so called eye wall. The convection of eye wall is like coming up, but slightly tilted outside. That's why it gives you a little bit of like stadium shape of center of the hurricane. So satellite doesn't. So while visible satellite image is showing us most like a bird view of a hurricane, there are other types of satellite that can give us the vertical structure of hurricanes. For example, here I'm showing you the image from global precipitation measurement, GPMs. So we can see the GPM try to cut through, going through like a Hurricane Arthur. And let's get it start again, see if it comes back. Okay, here. Okay, stop. Maybe let's go up here. Yeah, here. Let's start here. Okay, you can see. So center of eye is the, so GPM is the precipitation measurement. So you can think this as measurement of moisture. And we can see the eye is clear because there's usually no no cloud, no convection at the eye, and you see a strong eye wall. And while it's not easier to see, but you can still see a little bit of steady impact. And around the eye, you can also see the strong eye wall convection. So let's continue on to look at the Arthur. So for Arthur, you can see this is a range of 200 kilometers. So from the one edge of green color, which is the edge of convection, to the other edge of green color, Arthur is like about the size of 5 to 600 kilometers. And if you look at the eye to the edge, is probably like 250. And in terms of tropical cyclone convection, can be as high as 8 or 10 kilometers in height. So that's usually the depth of troposphere. Yeah. Okay, now let's just kind of have a schematic diagram of this vertical projection we are looking at. And why I'm looking at it, because now we are going to talk, we are entering talking about the tropical cyclone and its interaction to the environment. So where the tropical cyclone get the energy from? The answer is the warm tropical ocean. So ocean is the primary energy source of hurricane. So if you remember in the earlier rotational, like animation movie I show you, so we can see the primary like a counterclockwise rotation. But I don't know if you notice the rotation is actually like the rotation inward. So they are gradually rotation inward. Sorry for the not very speed, like a smooth speed. So the air circulation or what you see here, the gradual rotational inward, is because of the balance between centrifugal force and the pressure gradient as well as surface friction. So this is like the balance of the dynamic process in hurricanes. Throughout this process, there will be a inward push of the air parcel moving from outside of hurricane to the eye of the hurricane. And this is what we so-called secondary circulation. So the secondary circulation is important is because as the air parcel near the surface, near the warm ocean surface, moving from outside, moving towards the eye, they gain energy through the air-sea interaction. And the energy is then released through the upward convection as latent heat, and that deepening or strengthening hurricane. And then the air parcel continue and gradually move back to the background environment. This process is a positive feedback. What it means that once the tropical cyclone system or tropical system, they start to have the formation of this organized rotational system, they can actually continue intensify until they make into the area that the environment is not favor, or they are no longer able to gain energy from the surface, such as when they make landfall, they no longer get energy from the oceans. So scientists from IT, Kerry Manuel and Biston and Emmanuel, like in the 1986 and 2002, they simplify this, they explain the process and simplify this process as the equation we're showing on the left. What it says is, giving a sea surface temperature and the temperature and the type of the outflow layer, or sometimes we can just say is double tropical temperature. Then we can through calculate the physical process in this secondary circulation, we can know what's the highest intensity of a tropical cycle. So the image, this image is important is because it basically tells you there are two very important parameters that controlling tropical cyclones formation and intensification. That is the temperature at the ocean, sea surface temperature, as well as temperature at the top of troposphere. So the next one I just want to say, now let's move on to what is necessary condition for tropical cyclone to form. I have been telling you that one of the very important parameters is sea surface temperature. A threshold of tropical cyclone to form in the current climate is roughly 26 degrees Celsius sea surface temperature, because your ocean has to be warmer than atmosphere in order for atmosphere to gain energy from the ocean. And that is also why tropical cyclone is the feature of summer hemisphere. So the image on the left is showing you the SST in August, and while the image on the right is showing you the sea surface temperature SST in January. You can see the warming sea surface temperature is in the warmer sea surface temperature that above the threshold is in the southern hemisphere. So the next important necessary condition for tropical cyclone to form is so-called weak vertical wind shear. So what does the wind shear mean? So just thinking for less tropical convection, they look like a deep cloud. Vertical wind shear is the change of wind direction with height. So if there's a stronger shear, that's just one of the example. It can be the other way. It can be lower shear on stronger wind on the bottom, but here just an example. So if there's a stronger shear, then originally very aligned convection will get killed. And if it is even stronger, then the convection probably will be killed because the shear will bring some kind of dry air into the convective cloud. So the second necessary condition for tropical cyclone to form and to intensify is the weak vertical wind shear. And again, that's also one of the reasons why in the summer, the environment condition is good for tropical cyclone to form, because in the winter time, over Atlantic main developed region, we can see there's a very strong vertical wind shear as showing figures on the top left corner. So other than that, we also need Earth's rotation, because after all, tropical cyclone is a rotational system. So you need to have initial push of rotation that help the individual convective system to organize, and therefore get into the secondary circulation image I showed you earlier, get to those positive feedback process that continue to intensify become tropical cyclone. It's also need to have sufficient moist environment that's just more favorable for convection to happen. And also some like a lower troposphere relative vorticity like tropical wave. Those are again is to help the convective system to have initial like a organization, get organized. So I kind of explained to you that there are important parameters that controlling the formation and the intensification of tropical cyclone. What does it mean is that if we know what these parameters will look like in the upcoming season, we can use them to predict how active the season will be. So what control those parameters exactly? I'm not sure, have you ever heard El Nino's Southern Oscillation or ENSO? So this is one of the climate modes that control the above parameters at the seasonal time scale. So ENSO is a feature that you have warm Pacific warm pool at the central to western part of the Pacific in a neutral condition. and that induce overall very high, like active tropical convection in the central to western Pacific, and then a descent in the eastern Pacific, and also a convective system, more favorable for convective system for the Atlantic basin. But year to year, interannually, the location of where the Pacific warm pool will shift. When it shifted towards eastern, like central to the eastern part of the Pacific, we call it El Nino condition. And in the El Nino condition will be favorable for tropical cyclone to form in the eastern Pacific, but then it will result in fewer hurricanes due to the stronger vertical wind shear induced by the shift of the Western Pacific warm pool and the shift of the circulation, which we call the Walker circulation here. In the opposite, when there is a La Nina condition, means the Pacific warm pool move further towards west, they will give us more hurricanes due to in Atlantic due to the weaker vertical wind shear and also less stable atmospheric. So now if I ask you, say, so we know CPC is predicting above normal, 60% of above normal hurricane season. What do you think they are based? There's one primary factor is based on the prediction of ENSO state. So this is IRI CPC. So IRI is also an institute at Columbia. So this is IRI CPC ENSO forecast for 2021. They issued in May. So we can see start from May, June, July. There's a spread of models, some from the dynamic model, like weather prediction model. The other one's more from the statistical regression system. So there's a spread of the model forecasting. So that means that the model doesn't really, that it can be more close, that means it may be more close to neutral. But if you look at the CPC forecasting, they predict neutral or more towards La Nina as we getting into the peak hurricane season. And then if we look at the NOAA's prediction and the reasoning in the NOAA website, they definitely mention ENSO neutral and La Nina supports the condition associated with ongoing high active era because of weak vertical wind shear in our area in the Atlantic. And they also say the predicted warmer than average system temperature is one of the reasons. And then weaker tropical Atlantic trade wind and enhance the monsoon that provide the initial push of the vorticity, like tropical waves that help to organize the systems. So in addition to CPC and our CPC's forecasting, of course, like also use several objective guides. They are from different operational center, different global climate model group, as well as some like university group. But here just showing you a list of the group that provides the forecasting, and you can see they all project above normal. So normal is the orange dashed lines here. Then most of them have a consensus that we are expecting an active season. I think I can, so I have only a couple slides left, but let's just finish it. So what do we have crazy to the 2020 season? I actually means to use this as a question for whoever attendees to think. So first of all, one of the reasons is because the improved technology allowed us, and the change of definition allows us to start to looking into the early formation of tropical cyclones in May, and even though they only last for 2 days or less, we still consider them. But apart from there, there's also record high sea surface temperature over Atlantic. Here is the main developed region in that where the tropical cyclone most likely to form in Atlantic and also Western Atlantic area. You can see the temperature is 0.5 degree higher than average. in the Western Atlantic is almost 1 degree higher than average. And then the second one, I believe you can think is because we have a very strong La Nina event. How strong the La Nina event will be this year, we will need to wait to see. So far, it's probably expect to be La Nina year, but they don't expect to be as strong. So that's why they were also saying that while they expect a very active season, they don't expect as active as 2020. So I think that's all I have for today. I hope after the lectures you can describe how hurricanes looks like, and you can answer a question like what are the important factors controlling seasonal tropical cyclone activity, and maybe if someone talk to you about NOAA 2021 hurricane outlook, you can explain to them why. That's all I have, and I'm happy to take questions.
All right, great, thank you. So Chia-Ying, before we kind of go over to you for questions, I'm going to have Rosalba from our NASA GIST group join us and share some relevant NASA resources around hurricanes. So Rosalba, if you are, actually, Chia-Ying, can you stop sharing your screen and then we'll switch over to hers? Thank you.
Yes.
Great.
Great. Thank you so much, Cassie. Can you see my screen?
Yep, perfect.
Hello, everyone. So my name is Rosalba Giarretano. I help support NASA's Office of STEM Engagement at the Goddard Institute for Space Studies in New York City. And I am very happy to share about some supplemental resources about hurricanes. I am going to try to put some links on the chat. Okay. So today I would like to highlight the following resources: NASA Eclipse, the Scientific Visualization Studio, Earth Observatory Kits, the NASA Disasters Mapping Portal, and NASA GPM Precipitation Education. So the first resource, NASA Eclipse, is basically a series of videos designed specifically for students. And so the link that I shared with you specifically is to a video called Hurricane Hunters. And so with that video, you can learn about how scientists collect data that they then use to predict storms. There are many more videos, so definitely a resource that you should check out. The next resource is the Scientific Visualization Studio. So this studio works very closely with scientists in the creation of visualizations, animations, and images that help us better understand the Earth and space science research activities at NASA and within the academic research community supported by NASA. So this studio has thousands of videos that you can view, and you can also download for free. And the link that I am sharing with you specifically is for a visualization of Hurricane Maria in 360 degrees. So it's a pretty spectacular visualization. And as you know, Hurricane Maria devastated Puerto Rico. So the NASA Japan Global Precipitation Measurement Core Observatory satellite captured a 3D view of this storm. So with this visualization, you can go inside of that hurricane. The next resource is Earth Observatory Kits. And so this is written for students ages 9 to 14. And basically it has articles and images and hands-on activities and do-it-yourself projects. So the link that I shared with you will specifically take you to an issue called Keeping a Close Eye on the Storm. And so there you will learn about how satellites track storms from formation, landfall, and the aftermath. And then there's also a hands-on activity for you to engineer your own tower and see if it can withstand the strong winds of a model storm. So that's pretty fun. The next resource is the NASA Disasters Mapping Portal. So the NASA Disasters Program promotes the use of Earth observations to help predict, prepare, respond, and recover from both natural and technological disasters. So if you go to this website, you're going to find story maps and tons of information, a lot to do with hurricanes. And you will also find the disaster dashboards. The one that I am highlighting on the screen is the one for tropical cyclones. So with this online interface, you can view, analyze, and download the latest near real-time and disaster-specific products. So definitely something for you to explore. Also a good resource for teachers. And the last resource is the NASA GPM Precipitation Education. So this is a website presented by NASA's Global Precipitation Measurement Mission, and it has many resources both for students and for teachers. So you can learn about the Earth's weather cycle, weather and climate, the technology and societal applications of studying them, and there's a specific section for hurricanes that you should explore. And that's it for me today. Thank you.
All right, great. Thanks, Rosalba. And we'll share all those links after the session along with the recording with everyone. So Chia-Ying, we had one question during the presentations, which was really about that IRI data set that you shared with us, and whether or not there's sort of a repository of these forecasts, how often they're published, you know, and how do we access those?
And so IRI's data is publicly available. Let me see if I can copy the link to you. Maybe let me read. So it's on the IRI website. You can type IRI and so for forecast. Then you can see their forecast, and there's a repository all the way back to. Let me Google. Let me just first type it. Yeah, so there's a repository all the way to 2002, I believe, even though I never looked into that early before. And also the format changed a little bit, but you can definitely look into the recent years in a similar format. Yes.
Great, thank you. And so one question, so for our viewers that are still here, if you do have any questions, feel free to type it into the Q&A box here. One of the questions that I think I often think about is, we read a lot about, especially around hurricane season as it's just starting, why storms might be more intense and why climate change is actually sort of why climate change is making it worse, or making increasing the intensity of the storms, or increasing the frequency of the storms. So I'm wondering if you can touch on, what the trends are, perhaps. And I know prediction is such a hard thing, and you do a lot of modeling to try and get accurate predictions. But if you could just comment briefly about sort of climate change and the role of climate change in tropical cyclones.
Well, so there are three. So scientists will look into how climate change impact tropical cyclones through observation, look at the trend. Sometimes the trend is not easy to find. We also want to based on theory, or sometimes even we see a trend, but if the trend cannot be explained by theory or cannot be backed up by the numerical model, then we will have low confidence. But there are three impacts that we are pretty certain about climate change on tropical cyclone. As you say, one is the intensity. So if you remember the cross-section, like a secondary circulation I show you, that the very simple equations of showing you what's the strongest intensity a tropical cyclone can reach, just giving that to surface temperature as well as the top of troposphere temperature. Then you can see as the surface temperature increasing because of the global mean temperature increase, then you increase the highest intensity of that given storm. When the highest intensity is increasing, then means you have a chance to reach a higher intensity strength. So that simple equation is actually one of the is our theoretical argument to why hurricane is getting stronger. And we do see this in the trend, but you only see like in extreme value. The other two is we know tropical cyclone precipitation is going to be more heavier, means the precipitation rate at a given hour is going to be heavier. That is simply because the warmer air can hold more water vapor. And the system like tropical cyclone is very efficient to squeeze all those water vapor out.
Okay.
So,
I like that analogy. I like
Yeah.
that comparison. Yeah, that's helpful.
And the last one is independent to tropical cyclone, is the sea level rise. But because tropical cyclone, one of the hazards caused by tropical cyclone is a storm surge. So just imagine thinking of the original layers, 2 feet height of storm surge, but if sea level rise, then your 2 feet will become 3 feet, 4 feet. So
yeah,
that's why these three are most certain. There are other things we are still in debating. Yeah.
okay. No, that's really great and helpful. We've got a question here. So first, how did you become interested in studying tropical cyclones? And what are some of the current focuses of hurricane researchers? And maybe for yourself, what are you currently really what is your area of research now?
So I grew up in Taiwan. I don't know if you guys know that place. If you if in the first image I'm showing you those like climatology of tracks, Taiwan is totally covered by those tracks. On average, we have 3 hurricanes hit that small island.
Wow.
Per year. So kind of naturally is something we are like unaware of and kind of get into it. And once I'm starting to in college, I was majoring in atmospheric science. And it became one of the topics I'm most interested in because it's kind of close to the life. Yeah. And my research right now is actually about the hurricane risk and the climate change. So it's similar, it's like along the line what Cassie, you were asking, how do I know how does climate change impact tropical cyclone? And so I study how does that make impact, and I convert the knowledge into a predictive system for risk assessment. So I'm looking at whether New York City is going to face more hurricane in the future or not, and what kind of property of the hurricanes New York City will facing in the future, for example.
Yeah, very important. We'd all like to know so that we can all prepare. And I think that's sort of the $1 million question, is sort of what your city, what your community, what those, these are, tropical cyclones, as you nicely laid out, they happen all over the world. We call them different things in different regions. These are global things that are happening, but what does that really mean for us in our daily experiences and our communities? I think that's just such an important part of the research, and there's still so much to know. Yeah, and we have some, thank yous and very great presentations and great resources. We've got one question here about whether or not there are metrics or indices that track the accuracy of the hurricane forecasts. So when NOAA puts out a forecast like they do, do we go back and say, well, yeah, you were wrong or you were right, NOAA? And, I think you made the comment about how models have improved a lot. How have they improved, and what can you do now with a model that you couldn't do, 10 or 15 years ago?
So to answer the first question, the answer is yes. We are definitely always like looking at the National Hurricane Center. Are you guys doing good? Look at the CDC. Are you guys doing focusing? Give us a good outlook. Yeah. So there's the indices usually. So there are 2 basic metrics we use to evaluate the tropical cyclone forecasting. I'm talking about weather scale prediction. That is the absolute error of the track. So for example, if today National Hurricane Center said 5 days from now, where the tropical cyclone will be, and then there's a longitude, latitude in that location, the position, and Then whether 5 days from now we see, oh, it is 100 miles away, well, not that bad. It is 100 miles away from the exact location, then that would be an error, and we'll take average of error. And as you said, tropical cyclone prediction is largely improved in the past, like in the past 10 or 20 years. Really, I probably should have reused the electricity figures, so I have it on hand, but I don't. It's you really see a clear decrease in the error in the recent years.
Okay.
And that is because of the improvement of numerical model, the improvement of computational power that allow us to run the numerical model at the grid spacing that can resolve hurricane properly. Not the fully resolved yet, but it's probably enough. And also our understanding of hurricane process is improving. The most important thing is the technology of observations. Satellite data and how we observe, and the reconnaissance, how we observe those data into the numerical model, that is big improvement.
Okay, that's really good to know. Yeah. So this is a great question, and I've often wondered this myself. So why do hurricanes have different names, and who gets to decide how they're named? Yeah.
World meteorological organizations at each region, they have regional centers that are responsible for forecasting of hurricanes in those areas. Okay. And in Atlantic and Eastern Pacific, that's National Hurricane Center, and that therefore they give a list of names, and their name will be official forecast name. And like in the Western Pacific, Japan is official, is the official meteorological organization there that provide names. Even though sometimes Taiwan may have different names, the Philippines may have different name, we will mark it, but official name is always from the specific organization that is assigned by World Meteorological Organizations.
I see. Okay. Yeah, that's great to know. And sort of one last question that I think I'm going to combine sort of these questions as we're running out of time here. It's about sort of preparation and sort of becoming better prepared to withstand perhaps stronger hurricanes or increasing frequency of hurricanes. What can cities do better generally to prepare? And then there was a question that was about materials. And so, you know, how you might build structures to better withstand this is more architecture, or but how might you better build a city or design or plan a city, and how might that city better prepare for these sort of future impacts now that we know a little bit more about the science behind them?
Well, so the preparation for upcoming event, there are different time scales. So in terms of building code, it's really on the urban city design. That's way before everything going to happen, or right after when the city get destroyed, you need to rebuild. That's when you need to think of how to make the building strong. Concrete building is always a good because they can withstand the high, like a Category 5 hurricane. Mm-hmm. That's why in lots of Asian country, at least wealthier Asian countries, they use concrete building. And also you try to build away from the storm surge, like a flood prone zone, to prevent the flood will causing it. So if you have a concrete building that can withstand the strong wind, and also you have strong like a hurricane shed or strong windows, then you don't need to worry about wind damage. And then if you are outside of the flood prone zone, then you don't need to worry about flooding. That's usually a good way to do it. Yeah. In fact, the National Hurricane Center moved further inland because
they have the information. They know what they know what to expect. They know that there's risks.
Yes.
It's really interesting because there's sort of building to withstand hurricanes, but and then there's building to withstand flooding and sea level rise. And there's, I think, a lot of places, especially along our coastlines, that are thinking about multiple risks at the same time, and preparing and building resilience, but then at the same time also dealing with sort of urban heat islands in cities and increasing temperature. So everything is very interconnected, and I think that that's a really important point to sort of take home. It's not just the storm, but then there's
definitely the urban planning and the sustainability development is a very important course for every city planning to take over.
Yeah, for sure. Well, great. Thank you so much for your time. And thank you for Rosalba for sharing those resources. As I mentioned, we are going to share the recording along with all the NASA resources with everybody who signed up and attended the session. Chia-Ying, any last pieces of advice or things we should watch out for this summer as hurricane season ramps up?
Well, so we are still in, so I would say get ready for, so have already start your hurricane prepare.
Okay.
That's the first thing. And then once you start to hear something, you can start to plan according to the forecast.
All right. So be prepared, everybody. You heard it here first. All right. Well, thank you so much for your time. And thank you to our viewers. And we hope to see you again for a future session. And have a great rest of your afternoon or evening, wherever you are.
Thanks, everyone.
Thank you.
Thank you.
Bye.
Bye.